Here's your bell ringer, so go ahead and get that done here in a couple minutes. Alright, so looking at these, we are going to be using trig functions. Okay, so this is the angle we're given on number 1. We're given that 54 work marker. We're given that 54, so you have to use the angle opposite, or the side opposite the angle. So we think of sine, cosine, tangent. It's actually going to be tangent, okay, because we want opposite over adjacent. So we'd have tangent of 54 degrees equals x over 14. So to get that, you multiply both sides by 14, so x is actually going to be 14 tangent of 54. Go ahead and plug that in your calculator, see what you get. We got to change my calculator to degree mode. Should get 19.26. So x equals 19. We'll say 27. 19.27, and we are in centimeters. Okay. If you have one of the graphing calculators and you used it to do this, you have to press the mode button and make sure you're in degree mode because we're using degrees here. If it's in radian mode, then you're going to get a different answer. I think you get like 9.4 if you're in radians. All right, next one over here, number 2. So we have this angle there we're trying to figure out. So we have two side lengths. We have the adjacent side length and we have the hypotenuse. So we're going to be using cosine. Cosine of x. We don't know what x is, but we know that our cosine is going to be 34 over 78. And think about how we get that x back out. How we figure out what that is. All right, we have to use inverse trig function. We have to use inverse cosine of that ratio, and that's going to give us our x. All right, so inverse cosine of 34 divided by 78 gives you 64.16 degrees. Okay, a little bit of trig review, or geometry review rather. So lesson for today, we're doing 8.1. That's Introduction to Regression for Linear Data. All right, so we're dealing with scatter plots and line of regression. You guys have done this before, but we're going into depth a little bit more now. And if you've taken data analysis, you've done this stuff before. All right. So first thing we're looking at here is a scatter plot. Okay, you guys have been seeing scatter plots since you were freshmen in high school, maybe even 8th graders. Okay, but this is a scatter plot of the time spent on an exam versus the grades you get. So there's a correlation here, is if you spend more time on the exam, okay, taking your time looking over everything, you're going to get a higher score on the exam. All right, so that's not 100% true all the time, because if you see down here, we got, let's look at this point right there. We have about, I don't know, 40 minutes maybe, 40 minutes spent on the exam, and we have one person here that got a 67-ish, okay, and they spent about 40 minutes, but then we go way up here, one person spent about 40 minutes on it and they got almost a 90, okay, so maybe like an 88. But we have to look at the correlation of the data here, like is it a good correlation or not? I would say that it's decent, because if we draw a line through there, the data kind of matches a line, okay, you can kind of, if you put those points a little bit closer together. So if you guys remember correlation coefficients, that was usually given by R. That was how well the data fits a line. The one that we're looking at here, okay, with the line I have drawn through it, we say that that might be like a half, okay, maybe like a 0.5. Okay, first of all, it's positive, so it's going to be a positive 0.5, but remember when we do correlation coefficient, we use values from -1 to a positive 1. Okay, and if you get closer to a -1 or closer to a positive 1, that is a good correlation. That is a good fit for the line. Okay, so if I had data like this, that would probably be a positive 1, because it's really close to a line. and it's going up. The data is going up. If we go down like this, that would be more like a negative one. Right? If we have another one off to the side here where your data is just like completely scattered, that's like a 0. There's no correlation. Okay, you guys should remember that from Algebra 2. All right? So just in general, looking at data, you can tell how good a line is going to fit that data. Okay, so when we actually do that line of best fit, that's called the line of regression. Okay, we called it linear regression before, but we use line of best fit more often in Algebra 1 and Algebra 2. Now we're going to be using linear regression or line of regression. Okay, so go ahead and write these down here. So the line of regression best represents the direction of the data. Okay, so it's a line right here, pretty much like the one that I drew on the last slide. And we can use that line to find patterns and make predictions about the future outcome. So I mentioned this yesterday. We have a couple terms. We have extrapolation and we have interpolation. Okay, extrapolation means to predict outside the data we have. Okay, make predictions outside the given data. So you can think of interpolation, that's just the opposite. So we make predictions inside the data. Okay, so what does that mean to make predictions outside or inside the data? Well, this graph right here, all these scatter plot points, that would be the data that we're given. So anytime we make a prediction inside this area, okay, probably within the range of this point, maybe from 0 to 56 minutes, that would be interpolation. If we try to go beyond that, that's extrapolation. Okay? And extrapolation is sometimes where you have to say, does it make sense? Is it really possible to do X or whatever you're looking for? All right? So I want you guys to pause the video, and then we're going to go to a different video, and you guys are going to learn how to plug in values in your calculator and do a linear regression on your calculator, and then we'll come back to this example. So please pause the video and go to the other one. You can pause the other video whenever you need to. If you need to rewind, that's fine, but it'll be available. I'll send it to you guys in an email so you can watch it later also. Okay, now that you're done watching that video, I want you guys to try to plug this information in your calculator. We're going to do a linear regression of this information. Okay, so we're doing a turkey farmer here, and we are doing the weight of turkeys over time. So we have X is our months and Y is our weight. So it's the weight of the turkey depending on how old the turkey is. So go ahead and make two different lists. Okay, we got list 1, list 2. You might have to clear out your old lists like they did on the video. Okay, you highlight the L1 on the top or the L2 on the top and you press clear, and it should clear that list for you. Okay, but go ahead and enter these in the list. See if you can graph them and make a scatter plot of them, and then we're going to do a linear regression of them to get an actual line. So pause the video, go ahead and do that. Okay, now that you got those entered in and you graphed it, your graph should look something like that. Okay? And then we are going to try to calculate linear regression. Okay, so you go to Calc 4, you should press linear regression just like they did on the video, and make sure you're using your X list is L1 and your Y list is L2, and you press calculate. Okay, once you press calculate or you press enter, it should give you an equation. Okay, so this is what you would get. You would get it'd be A equals 1.4, B equals 3.8. Once you do that, you have to turn these into a linear equation, which is that right there. Okay, remember our general model for a linear equation is y equals ax plus b. You're putting a where it goes, you're putting b where it goes, then you're going to graph a line. All right, so go ahead and do that. Once you have your line graphs, you would go to y equals, you type in the equation 1.4x plus 3.8. Once you have that line graphed, it should look like that on your scatter plot. So these points might look more like little squares than circles. You can change that if you want to. It doesn't really matter for this purpose. Okay, but your line is going to look something like that. So if we're thinking correlation coefficient for this data, just kind of an estimate, I would say probably closer to a 1 because it's a pretty good data. It's a pretty good set of data. If we wanted to get a better estimate, I would say maybe like a 0.8-ish, maybe 0.85, because it's not too far off the data. Okay, your graph should look something like that. Now we're going to use that to figure out some extra pieces of information. Okay, so remember our equation that we have is this. Now we can use that to extrapolate or interpolate. Okay, could you use this linear regression to make reasonable predictions? Well, I would say yeah, because the data fits pretty well. And sorry, you guys can go ahead and you can pause the video if you needed to, jot this stuff down quick. Just try to abbreviate. Okay, that way you got something to follow along in your notes. So, number one, what is the weight of a turkey in 16 months? Okay, well, our data goes up to 14 months, so that means we have to extrapolate and figure out what 16 months is. Okay, X is going to be our time. X was our months if you wrote down that chart. Okay, so that means we're going to plug in 16 for X. So it looked like that, and we just simply plug that into our calculator and get an answer. And you get 26.2. So a turkey that's 16 months old weighs about 26.2 pounds. Okay, and it says, how long would it take to raise a turkey to weigh 30 pounds? Excuse me. Well, our weight, we're trying to figure out a weight of 30 pounds. We don't know what our time is, so we do know our weight. And remember, our weight is y, so if we plug it in, 30 equals 1.4x plus 3.8. Well, now we can actually figure out what our time is just with that equation. All right, so we're going to do 30 minus 3.8. Okay, we'll subtract that 3.8 from both sides. So now we got 26.2 equals 1.4x. Divide by 1.4, and we get x equals 18.7. So that means it takes about 19 months. Okay, then now our next question is, how many months would it take to raise a turkey to be 100 pounds? So we're going to do the same thing. 100 equals 1.4x plus 3.8. Okay, so you do 100 minus 3.8 divided by 1.4. You get x equals 68.7 months. So about 69 months. Now, the question you ask yourself is, what's wrong with this? What's wrong with the data? Or what's wrong with the question, really? Well, does it make sense? Are you going to have a turkey that's 100 pounds? Probably not. The other thing is here, while you might be able to, I don't know if genetic modification here in the future, you might be able to get a 100-pound turkey. The other thing is that you got 68.7. Okay, you'd have to look up the lifespan of a turkey. That might be longer than a turkey lives. But the problem here is the 100-pound turkey. Okay, you're probably not going to get a 100-pound turkey, but that would be a heck of a Thanksgiving dinner if you did. So looking at the data, you have to make your interpolation or extrapolation based on that. Okay, so next thing I want you guys to do, I want you to pause the video so you guys can draw this example. Okay, we're looking at residual values. Okay, this is actually the graph that you had before. Okay, so if you have a graph on your paper that was like this already, if you copied this stuff from your calculator, that's okay. But we're looking at residual values. Okay, a residual, okay, that's the vertical difference between the point and the line of regression. So our line of regression is this red line right here. That's this thing that we did on our calculator. That's linear regression. Okay, your residuals are the difference between your point, so I'm highlighting this point here, the point and that line. So what's the distance between those? What's the y value between those? Okay, and we're going to calculate that here in a bit. So the difference is written like this right here. So it's y minus y hat. That's how you say that. It's y minus y hat. That gives you the residual values. Okay, and y hat, we calculate that with our linear regression equation. Okay, so your line of regression minimizes the difference, making the most efficient line. So you want your residuals to be smaller. Okay, residuals, oops. We'll just say the smaller the residual, the better fit the line. Okay, so your residuals, the smaller your residuals are, that means that you have a better fit line. All right? But your residuals, you guys just need to know that that's the vertical distance between your point and the line. So how far is that? We're going to calculate that here. All right? So here we have a chart. I want you guys to copy this chart down. So pause the video so people can copy this chart down, please. So looking at these, we have our equation. Okay, we're finding the sum of the least squares here, right? So to give us the information about how good our line of best fit is. So our equation that we used was this one. Okay, and I'll go back to this again. Sum of least squares. Okay, that's used a lot in other statistical calculations, but this basically tells us how good our data fits the line. Okay, in general. There's a lot of other different explanations or sum of least squares, but we're going to use this, and I think we use this later on to calculate standard deviation, okay, which kind of gives us a plus or minus value. But it just tells us how good our data fits the line. So the equation for the line was that 1.4x plus 3.8. This is our turkey stuff still, our turkey values. So we need to figure out what y hat is. Well, y hat represents our line of regression here. So to get the values for y hat, we're going to plug these values into that equation. Okay, so we'd have y hat equals 1.4 times 2 plus 3.8. So that means the first one is going to be 6.6. Okay, then if we do the second one, so 1.4 times 5 plus 3.8, that's 10.8. Okay, so go ahead and fill out the rest of that chart there. I'll put those back up there. 6.6 and 10.8 were the two that I just erased. Okay? So if we were to finish out the chart, you'd get 6.6, 10.8, 15.0, 19.2, 23.4. Okay? So now what you're going to do is you're going to take this column, the value from this column, and you're going to subtract it from that column. So it'd be 7 minus 6.6 for the first column, or first area up here. Okay, so 7 minus 6.6 is going to give you a 0.4. And now we do 9 minus 10.8, so that's negative 1.8. And you can do most of these in your head. Some of them are pretty easy, some of them might be a little bit harder. Okay, so fill out the rest of that chart. Okay? So after you finish that one out, these are the numbers that you should have. And now this last column here is the same exact thing as this column, but you're squaring everything. So you're going to have to put these in your calculator, and you're going to square each one of these values here. So go ahead and do that. Square those and fill out your last column there. Those are the values that you should have. 0.16, 3.24, 9.0, 4.84, 0.36. Okay, so this chart right here is what we're going to use to calculate the sum of least squares. Okay, or sum of our residuals, sum of the residual squares. Okay, so we have our x column and our y column. Those are just what we started with. Our y hat, remember that comes from plugging all of those values, all the values from the first column into our equation. All right, and then we have this column here where we just subtract these two. You subtract those two columns from each other, and then that gives you this column. And then our last column here, we just squared everything we had here. Okay, squared all those values there. So now what I want you guys to do is I want you to add all these together. Okay, just put all those values and add them together in your calculator. So when you add them together, that should give us the sum of the squares of the residuals. Okay, so 0.16 plus 3.24 plus 9 plus gives you 17.6. Okay, so that's sum of the squares of the residuals, and that's what that is right there. So we're going to use this number later on in our next calculation. Not today, though. So that tells us the sum of the squares of the residuals. The smaller the number here, the better the data represents the line. Okay, so a smaller number here is good. All right, so that is the sum of the squares of the residuals. So this chart, you guys are going to have to do something like this on the test and possibly a quiz here coming up. Not sure when, because we'll kind of have to look at the days, but you want to be able to do something like that. Okay? So again, here's your data, just to double check. All right, so looking at this line here, okay, the regression line is a line that makes the sum of the squares of residuals a minimum. Okay, so go ahead and copy these down here quick. You can abbreviate. So what this means right here, this paragraph right here, that's pretty much what I just said. The smaller the sum of the squares of the residuals, that stuff right there, the smaller that is, then the better the line of best fit. Okay, so that's why they call this the line of best fit. Best represents the data. If your sum of squares of residuals is small, then that means you have a good fit for the line. Okay, the smaller the better. All right, there is your assignment, you guys. 1 through 5, it's not a huge assignment, but it's going to be kind of doing the same stuff of what we did on the examples here. So making these charts and trying to find some of the squares of residuals and calculating residual values and stuff like that. I sent you guys this video in the email if you need to go back and look at everything. But just send me some emails if you got any questions. I should be able to answer emails while I'm at the track meet. All right, good luck.